Hello folks, this is Arman with MetaSpec. Thanks for joining. This is going to be the workshop for solving our email forensics capture the flag competition challenges 1 through 5. If you get good audio and everything is working okay, it will be good to have some feedback on the chat so we can get started. So I know this is about the competition mostly, but I will kind of treat this as a general email forensics workshop. So we will go over the challenges individually from start to finish, and we will assume that some of you have not really spent the time doing the challenges or looking at the solutions or anything like that. So with that said, let me share my screen and let's look at the first challenge and go through them and solve. And if you have any comments or questions, feel free to drop them on the chat, and I'll be happy to answer them. So let me share my screen here and open the let's see, let's get a new browser window going here, and let's get the challenges. So let's start with the first challenge, which was to read or not to read. So I'm going to try to read the wording on these challenges pretty carefully, because there's going to be some nuances there that are kind of important. So let's read it carefully. So it says you have exported the contents of a Gmail mailbox via takeout, so Google Takeout. Look at the exported data. You suspect that one of the top level messages may have been read by the perpetrator. Enter its message ID, that is the value of its message ID header field as defined in RFC 5322. And there's a download here, and there is a SHA-256 hash. So let's actually open a folder. Let's make a new folder here. Let's call this solutions 1, and let's download our file here. All right, let's go get the hash of it. SHA-256. Let's bring this into view. Yeah, that looks good. So let's extract that file. So this looks like the structure of a Google Takeout, except it's missing some of the metadata stuff. But let's open this up with something like a text editor. Perhaps it's about 125 megs, so it's not tiny, but it's not huge either. So let's open that up in something like Ultra Edit. All right, so it looks something like this. So there's a bunch of messages, essentially mbox formats are concatenated together. So these are going to be my messages in RFC 5222 format. So the wording of the question said that you suspect that one of the top level messages may have been read. So how can we get information about messages being read when we don't have external logs or metadata about the messages? We're not going to find that in the body of the message most likely, or in the headers. So one area that might help us here is that when we look at the header fields, there's a Gmail labels header. So there's a listing of Gmail labels as exported by Takeout. So let's take a look at what those Gmail labels look like. So I'm gonna start by doing this in a text editor first, so that it's accessible to everyone. And you'll see that we'll use a few tools going through the challenges. When I use, in this case, I'm using Ultra Edit as a text editor. You could substitute with a free text editor like Notepad++ or something like that. In some cases, I'll look at DKIM and ARC signatures, and I might use forensic email intelligence for that. You could do the same type of analysis with something like DKIM perhaps, and we have a listing of, actually if you look at the beginning of the capture the flag page, there's a list of tools and tool recommendations here, so you can check these out, and there's essentially a freely available substitute for just about anything. So with that said, let's start with the labels. So I'm going to search for this line to get a listing of all these lines here. So let's do a quick search for Gmail labels, something like this. And let's copy this to a new file. So this is kind of like a dump of all my Gmail labels from all the messages in there, presumably. So I noticed that at least some of them say unread. So let's see what the situation is there. So 1812 matches for unread. So it looks like based on the labels, they all appear to be unread. So what would be a label that could tell us that the message has been opened at some point or has been read at some point? So what I'll try to do is, it's not very clear to me right now just by looking at this, what the tally of all the labels are. Like, are there some other labels that are interesting, for example? So I'm going to try to get a list of them. So what I'll do is I will take out this part, and then let's assume that there are no commas within the labels for the time being. So let me just replace the commas with a new line and then sort this. So I arrive at this list of labels, and one of them jumps at me right away that there is an opened label here. So open label, you can research this, that points to that file having been opened. So if there's a combination of opened and unread, and that typically tells you that the message might have been opened and read and then perhaps marked unread after the fact. So let's try to see if we can locate this open label and how many of them we have. So we have only one, and the Gmail labels line looks like this for that label. So I'm going to go find that line, and here's my line with the open label. So if I go and look for the message ID of that file, which is essentially what the question is asking for, here's the message ID. You could enter this with the brackets or not, and either way it should work, but this will be the answer for that. Now I'm going to do this a second way, because I'm going to look at this specific file that we're interested in. So I will make an FEI project out of this. So let's call this T1, something like this. And let's see here. Let's put this in a folder here to ingest. And get this going. So this is essentially going to break the mbox down into the individual messages there are, and then I'll have a look at the labels that way. So it'll be a little bit quicker to get to the solution, but I also want to look at the individual message in more detail, so it's going to help me a little bit there. So let's open this up in grid view here and go look at the Gmail labels again like we did earlier. So here you can see a tally of these, and I'm going to focus on this open label. So this was the message that we're looking for again, so we could go copy our message ID from here. So we found it. Now let's move on to the second part of this challenge. Let's see if that's available here. It says, congrats on finding that message. You're now examining the message you identified during the first part of this challenge. One of the header fields gives you pause about the authenticity of the message. Which header field is it? Enter the name of the header field, including the column. So apparently there's a header field that is problematic there. So let's open that up. You could look at this message in a text editor, like I said, so it could be, for example, something like Atom with the EML language, or Visual Studio Code with MIME highlighting or something like that to help you go through it. So it looks like, let's take a look at the appearance of it. I'm gonna show these remote images too. So it's a message from Next Draft, and the body's not that important right now. One thing I noticed here right away because of FEI is the content length mismatch, so that's something to pay attention to. But I would first probably check the DKIM and ARC situation here. So in this case, what we're seeing is that DKIM is failing, and there are actually two DKIM signatures that are both failing, and the ARC chain is valid. So we need to think about, number one, is this a problem? What does it tell us, this configuration we have here, and is this our problematic header field? It could be DKIM signature, for example, which could be. So that could be one of our possibilities. How many attempts do we get here? I think it was 3 attempts or something. I don't see it there because I think in the archived version we have unlimited attempts, but you did have a few attempts here, so we could try DKIM as an easy first attempt since it's failing. But I would want to look at, number one, some comparisons from the same sender to see if we have some control messages and do they verify DKIM and ARC. And we have this content length mismatch. Is that the situation for them as well? So content length, just to refresh your memory, was the byte size of this entire payload of the message. In this case, we see right away that the calculated content length is 120,915, and the advertised one is shorter than that, so that's kind of a problem. So you know, when you look at the header fields, you'll see generally that this is consistent with something that was sent from a mass marketing solution, in this case MailChimp. There's a campaign identifier, some abuse-related things. There's a list ID. I'll cheat here to cut to the chase quickly and actually look at the insights from FEI. It says that there's a failed DKIM and ARC signature. That's fine. Delivery of the message took 45 minutes. So that's something to take into consideration. Is that a red flag here? Given the fact that this is coming from a mailing list, that's probably all right. It could have been that it was, you know, composed a while back and then scheduled to be sent, and it took a while to actually transmit the message. So I think that's fine with me. There's an issue with the content length mismatch, which we already identified. Xmailer suggests MailChimp. That makes sense. This header field suggests distribution through a mailing list, which we already figured out. The from email address does not match the return path. So is that a red flag to consider? So there's a different return path on here. Could that be our field that gives us pause? Well, I think not, because this is a legitimate use case for a different return path. If you are sending messages through a marketing solution like MailChimp and you're broadcasting to thousands of people, most likely you're not going to want all your NDRs, the non-delivery reports, to come back to your main mailbox. And MailChimp actually doesn't want that because they want to process those reports. If there's a hard fail, they want to know that that person's email address is no longer valid. They want to take them off the list. So they set up this separate, bounces email address specific to that mailing list or tenant, and all the returns go there essentially. So in this case, that makes sense to me. I wouldn't have a problem with that. So mainly I'm concerned about the failed DKIM and ARC and the content length mismatch. Now looking at the DKIM and ARC, we see that ARC verifies and DKIM doesn't. So that's kind of interesting. So there are, let's see here, 2 DKIM signatures, one of them with the domain davenetics.com, one of them is another domain, presumably MailChimp related domain. So those fail, but the ARC chain verifies. And when you look at the ARC chain, so we have this ARC set here. This is the first set based on these, based on the tag, the instance tag. you look at the chain validity status at the time that Google created the ARC chain, and it says that none, so there was no existing valid or invalid ARC chain at that time. So Google created it, and it's saying that at the time that it got this message, DKIM, this DKIM signature was passing, and this DKIM signature was passing. So Google claims that when they got it, they were both fine. So something happened along the way. So let's get into that in a bit. Let's see if, you know, how valuable that information is to us. But before we get into that, I want to look at some other messages from the sender. So we were looking at item ID 1058. So let's back up from here and let's find some other messages from this guy. So here was our message that we were looking at. So here's another one. And this also has the same type of situation. So ARC verifies and DKIM doesn't. So that's probably a common occurrence here, unless, you know, all these other messages have the same problem. So let me put the DKIM thing in the back burner, and I want to compare these two to each other to see how they look against each other. So there's obviously going to be a bunch of differences because they're different messages, so different timestamps, different labels. But I'm looking at structurally, you know, do they largely align, or is there something problematic here? And they do largely align so far. So they have the ARC signature, they have the authentication results. Here, this one, the other one has a temporary error, no key for signature on this one. So that was an issue with, this is not the message I'm interested in, but this is the other one. So that's interesting. So apparently there was no key available for that at the time that Google checked it. The DKIM signature makes sense and kind of lines up, although the signature length is a bit different looking. So let's move down to the received fields, the date, text mailer, report abuse, all that lines up. Same MailChimp user, is feedback ID. But one thing that doesn't line up here is that this message does not have the content length at all, this other one. So the one that I'm looking at has a content length, but the other one from the same example sender does not have one. And it actually doesn't make a whole lot of sense. If you are familiar with content length, it's something that you would see in emails that have to do with Yahoo or AOL. Typically they put that traditionally, and this is coming to Gmail mailbox, and it's coming from MailChimp. So I don't really see why that would be a content length there. So that doesn't make sense. And actually, if you were to explore the rest of the messages from the same sender, you're gonna see that there is no content length there. So that's our odd field here. Now I want to look at well, maybe we can talk about that later, but I want to explore the ramifications of this ARC chain passing later. Perhaps we can talk about it at the end, like what does that give us? That is actually pretty solid information about the message being valid at the time that Google got it. So that could be actually a positive point for the message as well. All right, so we got our message ID for the message we were looking for, and we got part 2, which was the content length header field that we were looking for. So we're good there. Well, one thing that we could explore there was also the availability of the DKIM and ARC public keys. Are they still available? And can you look them up at the moment? And you could at this time, so that's not a problem there. Let's take a look at our second challenge, Gulliver. So here it's saying that you're asked to examine an Outlook message. This message was found within an Outlook data store, like a PST file presumably, and differed from its neighbors as in the screenshot below. So when you look at the screenshot, there's all these other messages, and this specific one has a little closed envelope that's yellow. And it's saying that specifically, even when the message was read, Outlook displayed the yellow envelope icon next to the message within a folder. After analyzing the message, you found that a MAPI property is responsible for the above behavior, which MAPI property is it? Enter the 2-byte hexadecimal identifier of the corresponding canonical MAPI property. And there's a little hint there that this is going to be something from this to this value. So it's going to be something in that range. And it's going to be 2 bytes to help. So let's download this, this second file. So solutions, let's make a second one here. And let's go find that file. Let's actually extract it here. All right, so here's an MSG file. So what I'll do is, well, let's open this up again to see how it renders. Let's generally explore. So it is a pretty simple file from email from Ornat to FEC dev. There's an attachment there, and let's read the contents of the message. It says, "Hi there, I've been trying to extract a critical file from the attached zip. I've been told that the zip was recovered from a corrupt disk where some bytes within the first 24 bytes of the zip file could not be read. These unreadable bytes were replaced with zeros. Any chance you could extract the document inside the zip for me? Thanks, Ornat." So there's definitely some narrative there, but we're not interested in that right now. We want to see what this looks like in a PST or in Outlook, let's say, to see if we can reproduce that behavior. So let's do that. So let's get this message. Let me make a second copy of this message, and let me fire up Outlook and put it in there. So let's get a new Outlook data store going. So let's create a new data file. Let's put this under the folder where we were. Up. This looked pretty tiny. All right, so here's my Outlook data file. Let's open up Outlook. This is another test account here, so I'm gonna make a new folder here called test. And while I'm in that folder, let's go find our second copy of this message and drag it in there. Oh yes, and we see that what that screenshot was talking about. So there's a little envelope there. So when we look at this message, I'm going to open the other copy of it. It's talking about a MAPI property that's responsible for this. So I'm going to take a look at the MAPI properties, and you can look at them. It's actually only 75 properties, so it's not a really MAPI property heavy message, and you can kind of go through them fairly quickly. There's going to be a few about the attachments, timestamps. There's going to be a few about the timestamp information within the message. Most likely they're not going to cause this envelope situation. There's some information about the attachment of the message, which we can get into later, and we can explore if that's responsible for it. But if you look carefully, one thing that stands out, and it's right away close to the top, is the message class. So typically these messages have the IPM node class, which is like a standard email message class, but this has a different class. It says IPM node.std. So that jumps at me right away, and you might wonder, could that cause it? And if that's the case, then how do we verify? So we could try to change that. So let's go open up MFC MAPI, which is one of the tools that I had listed in the recommended tools here for the CTF. So let's log on to a new session and open up this Outlook data store that we have, root container, and the test folder, and our message. So we can see all the MAPI properties of the message. So, if you're not going to use forensic email intelligence, for example, you could do the whole analysis here and look at all the MAPI properties and all that. And I'm interested in this message class, and I want to see if I were to get rid of that. Would that change anything? And yes, once you get rid of the extraneous part of the message class, then it reverts back to being an ordinary message without that envelope. So in that case, it is our message class, and you can find the MAPI property identifier here, it is up to here, the first 2 bytes of it. You could write this with the hexadecimal indicator in the beginning, the 0x part, or without. Either way, the flag should work and you'll be fine. But that is what we were after. So done with Outlook. Let's close out of this Outlook data file so we don't get into trouble later. And let's look at the second part of this challenge, which was Gulliver part 2. It says, you now direct your attention to the contents of the message you examined in part 1 of this challenge. Extract the critical business document contained within GoatZip in its entirety and enter its MD5 hash. So if you remember, there was an issue with this attachment not working based on the body of the email. Now, we don't really trust the body of the email, but we will try for ourselves to see if it works or not. So let's save this out to solutions 2. Let's make a folder here called attachment. And let's try to extract it. Let's see what we can do here. Let's try the regular Windows Explorer extract. And it says an unexpected error is keeping you from copying this file. If you continue to receive this error, you can use the error code to search for help. So that didn't quite work with Windows Explorer. Let's try with 7-zip. That also throws some errors. There are some data after the end of the payload data, so that's something to keep in mind. Did it extract anything? Well, it did extract something, but it doesn't quite open. So that's probably partial at best. Now, there were a few ways to solve this, and if some of you have noticed that this wasn't an exercise about coming up with a zip file that's really hard to recover. So one of the methods could have been to probably use something like a zip recovery tool. There are some tools designed for that, and I've thrown this at a couple of them and they failed, but I'm sure a well-made one would have no trouble recovering this. Another possibility might be to use some libraries that don't really adhere to the specification very closely, and they extract it somehow, and I'll show you in a little bit how. Or you could try to manually repair it. So now I'm going to take kind of the more detailed road, I guess, to explore it fully, but just know that there's many ways, and this was kind of easy points. I'm sure most of you had zero trouble recovering this. So the body of the message was saying that there were some bytes in the front of in the first 24 bytes, right? Oh no, it wasn't here. It was in what we read in the text of the message. So let's read that again, and let's assume that it is correct for the time being, because it is a clue. It may not be reliable, but it might be a good starting point. So it says that there were some bytes within the first 24 bytes of the zip file that could not be read. These unreadable bytes were replaced with zeros. So let's pay attention to the first 24 bytes and see what might have been replaced with zeros there. So the first thing I would do is probably to open up the zip file format spec, and there's a copy here from pkware. And when you look at the header structure here, so it says the local file header should look like this. So there's going to be a header signature, 4 bytes, version needed to extract, general purpose bit flag, compression method, last modification file time, the time component of a date component with CRC32, compressed size, uncompressed size, and at this point we get to the 24 bytes, right? So this is 10, 14, 18, 22. We're getting over to 26 here. So it's got to be somewhere in this area where our replacement was. So you can actually get into this kind of manually and following the file format specification. I'm going to open this up with a text editor that kind of shows that pretty clearly. So I'm going to make a copy of this, as I usually do, and open with 010 editor. Some of you might have this, and this has a good template system where you can make your own templates or use some templates from other authors that kind of dissect messages and highlight different parts of them, which can be helpful for PDFs, for zips, or any type of file that you want to analyze. So I'm going to utilize that feature here to look at the different components of the zip file. So there's the file signature here. So if you look at what this was saying, the file signature is going to be 4 bytes and it should be 0403 4B50. So that is what we have here, 0403 4B50. This is Little Indian, so you're going to transpose the bytes here, but that is our signature, and if you render it, it looks kind of like that. So we have the signature right. I don't see anything that looks like it be replaced with zeros there. Version, that could have been, part of it could have been replaced with zeros, but if you compare to other example zip files that you could very easily create, you'll see that all this actually makes sense. This compression is deflate. There's a date time here. There's a CRC here, which could come in handy, so let's keep that in mind. There's a CRC, which is essentially a hash of the file. There's the compressed size and the uncompressed size. Now, if you look at the uncompressed size, half of it is within the first 24 bytes and the other half is out, and the out part has some zeros, but based on what Ornat was saying, if we believe him, that's not part of the affected area. So we should focus on this other part where there's some zeros here, and that could kind of explain the issue we were experiencing with 7-zip, because when we extracted it, it said something along the lines of, hey, there's some bytes after the end of the file, but if this was truncated, the compressed size, maybe it's not getting to the end of the file. So how can we work around this easily? Well, one thing we could do pretty easily, at least as an attempt, is to try to overshoot. So we could just fill this with something large like this and save it and see if we can extract that way. So let's see some more options. So we still get an error here. It says that unexpected end of data. So it looks like this time it reached the end of the data before it expected it. And there are some data after the end of the payload data. That's fine. It did extract something. So I'm not sure if what it extracted is everything. But there's actually a quick check that I can do before I actually go and submit this as a potential solution and waste my CTF attempts. What I can do is, if you recall, inside, let's ignore this. So inside this, that was a, not the signature, but that was a CRC value here, right? It was 90 CAFA27. So let's see if that matches the CRC of what I extracted. Normally, 7-zip would have done that. So let's show some more options and hash it. "90 CAFA27. 90 CAFA27. So very good there, it seems. It looks like this overshoot method kind of worked. So we instructed 7-zip to just forget about, in a way, the compressed size that's in there and just keep going until it reached the end, and it kind of worked. So this would be a way to grab the MD5 of the file and submit, but it's kind of a a dirty trick, I feel. Like, how can we be a little bit more precise and do it right? So if we look at this here, all the structure ends after the file name here, and then the body of the file starts, and then it keeps going, and there's a single file here, we know, and then here's the directory entry and the footer, essentially. So all this should be the contents, or the compressed contents of the file, and we have access to it, so we could figure out how long this is. So this is, selection is 369397, and in hexadecimal it is 5, so 05A2F5. So 05A2F5. So we could come over here, and we have the 05 here. We could put the A2 here and the F5 here, essentially taking what we find by manually observing the contents of the file and repairing the header. So let's see if this does us any good. So let's go back to this and make a second copy after we repaired. And well, this time it went without any trouble, so no complaints from 7-zip. So presumably, since it went any hiccups, you could assume that the CRC check went well. So 7-zip would have done a CRC check and checked that what it extracted matched the CRC within the zip structures. So there's no point in even doing that, but you could still manually verify that CRC hash. Oh, this is Windows 11 is driving me crazy there. So the CRC hash still matches, so we could grab this MD5 and use that as the answer to our challenge, and yeah, open as promised goats. So that would be the second method, essentially, by not overshooting but being a little bit more precise and attempting to manually repair the file. Knowing, I didn't show that part, but I would definitely, make an example zip file there and compare side by side which parts of the header match with my example file and which parts potentially could have been zeroed out, and that helps you be clearer about what to focus on, which parts are just flags and not really of issue here. So having done that, let's take a look at what's next for us here. So we did Gulliver part 1 and 2. Now we were getting into can't touch this. Let's take a look. Okay, it says you have forensically preserved emails from an Outlook.com mailbox in MIME format. One of the emails contains crucial evidence. Unfortunately, DKIM verification fails for this email of interest. Based on prior experience, you believe that the failure of DKIM verification is caused by changes that were made to the message body automatically by Microsoft's email server. Roll back Microsoft's changes to the message body by making as few changes as possible. So that's kind of important. As few changes as possible. So you could make this DKIM verify perhaps by making more changes, but we want to make as few changes as possible. And bring the message to a state where both DKIM signatures are verified. Once you get there, enter the total size of the resultant EML file in bytes. So essentially we're going to make some changes to our EML file until DKIM verifies, but just until it verifies, not further changes, and then get the size of the message, and that's all we're after here. So let's go to solutions again and make a new folder. Write this down. I think I forgot to do this in the last one, but of course you should hash these and make sure that the hashes match what we advertise here. So in this case is this 406940. Yeah, we're looking good there. So let's go extract this here. Write this down, EML. So let's take a look at what this looks like. And please keep this safe. We will need the info in a few weeks for the transfer, it says. All right. So there's a zip file there. We're not too concerned about the authenticity of the message, so I'm not going to get into too much of the, looking at the headers and all that stuff. But when you look at the DKIM results, there are DKIM signatures and both fail. So there's this guy and there's this guy. So based on the wording of the question, it sounds like these signatures should verify, but they're not verifying, we believe, because of changes that Microsoft's server made to the message. So here's how I would approach this. If I know that this is likely the case, then I would look at who this is coming from. So in this case, it's coming from a Gmail mailbox, and it's coming to an Outlook.com email address. So I would make an example message from a test Gmail mailbox that I have, and probably attach the same attachment that's in here and write down the same message body as it is in here, like this. and I would send that message out to an Office 365 mailbox, and I would BCC myself so that the copy of it comes to me as well. And then I would compare the copy that I got to compare the copy that Office 365 got to see what kind of changes that I'm seeing. So if you do that kind of analysis here, you will find that Office 365 actually changes a few things in the message. Let's go try to undo those. So this was our message, right? So let's make a copy of this. I'm going to open in a text editor. All right, so when you look at the contents from Office 365's processing versus what the actual sent message looks like, one of the things that they add is to the HTML body of the message, and they insert this additional meta tag here. So that's extra, and for some reason they also add a couple of extra lines. You would see this based on comparison of an example message that you sent to yourself basically, and see what's the difference between a sent item and a received item in Office 365. Now, having unrolled those, let's see if it verifies now. And it does. So those are the couple of changes Office 365 made automatically. And just keep in mind that that is kind of problematic, because in this case they were very simple changes and the message itself is very small. But if you have a message that's larger in body, for example, there's text encoding, there's coded printable or something like that, then that becomes like a snowball effect. There's going to be multiple changes all over the message, and once a little bit changes, then the encoded text changes in several spots, and it becomes a little bit hard to unroll that. But in this case it was kind of easy. We picked a message that was short in size and it could have been easily fixed that way. So just keep that in mind generally when you deal with Office 365. So let's get the size of this message. So now we're at 10,150 bytes, and that was the answer for this question. So if you notice, we made the bare minimum changes, so we didn't really mess with the headers. We just changed the body processing that happened to the message and went from there. Now let's move on to the second part of the message. Can touch this part 2. So first part, we were interested in the byte size of after we fixed the message where things were. Now we're interested in something else. It's saying, great work, you managed to roll back the changes and arrived at a message where DKIM signatures are verified. Currently the DKIM signature header field specified the digital signature algorithm as SHA-256, resulting in a body hash value of this base64 encoded string. What would the body hash have been if the algorithm were SHA-1 instead? It says, note 1, perform your calculation using the new message you created during part 1. So essentially this is going to be the fixed message, not the original message. And then it says, enter the body hash in the form it would have appeared in the body hash tag. So in this case, we're going to hash it, and then we're going to put it in this base64 encoded form. All right, so in this case, we're having to go a step further. Knowing the byte size is not enough. The question is asking basically, did you really repair the body, like as in everything is perfect, because we want to see that hash. So again, there's going to be a few ways to do this. I'm going to do it in 010 editor again, which makes it easy, but that will be many different options. So let's make another copy of this for that. And actually no, right, this is not the one that I fixed, is it? This is the one that I fixed at 1041, so I want to make a copy of this one. Let's call this fixed. Yeah, I almost hurt myself there. Let's make sure. Yeah, so we are verifying. And just as a reminder, like I said earlier, you could do these DKIM verifications with DKIM Pi. It is in the list of tools. You might have to juggle a little bit when there are multiple DKIM signatures involved, like this one. I think last I checked, it only did the topmost one, so you might have to shuffle them around to get them both to verify or check that verification, but just keep that in mind, so you don't need this to solve the challenge. but it just makes it easier for me and prevents the switching from tool to tool. So I'm going to open this up. Again, show more options with this guy. And so looking at the DKIM signature, so what the question says is true. So we have this body hash here with the SHA-256 algorithm. It's actually common between these two DKIM signatures, as one would expect. And the first thing I want to do is, can I, number one, replicate this body hash as it sits now, and then I'll worry about how can I calculate the SHA-256 version of it. So I'm gonna first do this with this editor, which makes things a little bit easier. So for the body hash, I'm gonna start by getting everything here, and I will get the checksum tool invoked here, and I'll pick both of those hashes, SHA-1 and SHA-256, that I'm interested. So I arrive at these body hashes, but the body hash here is not in this format. It's in base 64, and there's a little bit of a distinction there. It's not the base 64 of the string, it's the base 64 of that byte array. So you don't want to take this as a string and then base 64 that string, because that wouldn't work. What you want to do is you want to take that array of bytes and base 64 that. So if you were using something like CyberChef, then you would be interested in doing something like from hex to base 64 or something along those lines, which we'll get into in a bit. So I want to verify first if my SHA-256 actually results in that body hash that's advertised there. So I'm going to do a couple of tricks here. One of them is I'm going to copy this value. I'll open a new tab. And first I'll say paste from hex text. So this is going to pretend like my text was a hexadecimal representation of a byte array, and I'm going to paste that here. And then I'm going to copy this as base 64. And here's my body hash. So here's what I was looking for. So that makes sense. So for SHA-256, I'm good. So I'm going to do the same thing here for SHA-1. Again, I will paste from hex, and copy as base 64 and paste. So this is the base 64 version of that byte array, which will be your answer here. Now, this might feel a little too magical because this tool is doing a couple of nice tricks to get there. So let's see if we could do this with something like CyberChef. So it's a little bit clearer. So let's fire up CyberChef. Let's keep our editor here open too, because I want to see these hashes. So let's fire up CyberChef and let's get the body of my message here. So what was the part that we selected? This whole thing, right? So I'm gonna dump this here. And let's say if we do SHA-256, do we get what we're looking for? And we don't. So what could be the reason why we're not getting the body hash that we expect? Well, I'll give you a second to think about this while I take a sip of water. Well, it could be that maybe, in our email, according to RFC 5322, our line endings have the carriage return on line feed characters, so there are two characters back to back. But when you use CyberChef by default, your line endings are not going to be carriage return on line feed because it's not supported in this HTML text area that they're using. So you could set the options here to preserve carriage returns for a few options. You could only preserve for high entropy inputs. Our input was not high entropy here, so it didn't do that automatically. Or you can say always. So in this case, I'll switch this to always to see if that makes a difference. So I'm gonna. All right, so let's see if that matched up. Yes, you see 8344 EBA ending in B2A. So now when we preserve our our line endings and the cage returns and the line endings, then we're good. Now you can't see the pasted data, or you can't really interact with it because it's just treating it like a blob basically, which is fine. So how do we get to the base 64 version of this? Well, we could say something like from hex to base 64, and this was the base 64 that we had. So if we were to substitute that SHA-256 for SHA-1, would that, yeah, so that's our flag that we're looking for here. So it's essentially a copy of what we had through 010 editor. So you could have done this through something like CyberChef, or with a text editor or anything that you like. Now let's go back to the challenge to see where we were. Oh, so this was part 2 of our challenge, and we were looking for the SHA-1 version of the body hash. So we're good there. Now let's see next challenge. Next one was time machine. It says, and this does not have a second part, so this is going to be pretty quick. It says, you have located a key email message within the forensic image of a suspect's computer. Based on intelligence you previously received, you have reason to believe that the email message was altered after the original email communication took place. And exactly one complete sentence was added to the body of the message. So there are a couple of important phrases there. Number 1, exactly one complete sentence was added. And number 2, it was added to the body of the message, not to the header or anywhere else. So that's kind of important. So we're looking for one extra sentence, very good. And to that extra sentence, including the period at the end of the sentence. So it sounds easy enough. So let's make a new folder for this solution. Go back here. Solutions, make number 4. Let's download this guy here. And let's go find it and hash it. Okay, so SHA-256, let's compare that to what we were seeing here. 1B, yeah, I'm not reading all the bytes, but it is the same thing, so we're good there. And let's go. Actually, we can close out of this too. Don't need that for now. All right, so let's extract this. And let's take a look at what this looks like. Oh, wow, there's something interesting. So there's this extra line at the top of the header. So that's something to talk about, but let's ignore that for a second. So the message looks like this. So it's pretty straightforward. There's quite a bit of body content there. This is based on a novel, but I hope you didn't try to read and make sense of it, because it's kind of shuffled, so it would probably give you a headache there. But we are interested in finding this extra sentence, but let's look at the contents of this message header first. So it looks like it says my version 1.0, straightforward. There's a date, there's a message ID. This is consistent with Gmail API, which makes sense. It's from Gmail. So it maybe was from Gmail's web interface, something like that, to Gmail. But there are no transport headers. So it could be, so there's no DKIM signature, ARC signature, anything like that. It could be that perhaps this is the sender's copy. So maybe Ornat sent it, and this is the copy from his sent items folder. We don't know. But that could be fine, and we're not too concerned about that. And content type is plain text, and the character set is UTF-8, and there is no encoding specified. So we know that if there's no encoding specified, then this is not something like coded printable, but this is just 7-bit, so easy breezy. Nothing has been encoded here, which makes it very plausible. And number 2, there is no alternate MIME situation here, so there is no HTML version of the body, there's only the text version. So this was likely a plain text message, and it had simple enough characters that map server when somebody would request a message or a message body. So let's take a look at that to to see if we can recreate something like that. So I'm gonna do this. I will close these out. Let's show you guys. Let's just talk to an IMAP server real quick to see if we can reproduce something like that. So let's do, so I just fired up the Windows subsystem for Linux. So let's do OpenSSL as client and connect. We're going to do imap.mail.yahoo.com. So let's connect to Yahoo's IMAP server, a mailbox that I have as a test mailbox. And connected, life is good, server says hello, hello server. Let's log in as a test mailbox that I have. You've probably seen this from some of the CTF challenges. Login successful, very good. So let's list the mail folders there. Oh, you see some untagged responses already. See, we issued the command that required multiple lines of responses, and there's the untagged responses with the stars. So life is good. So let's examine sent. So let's open up the sent folder. Okay, we got 29 items, and let's do a fetch to kind of reproduce what we were seeing there. So let's fetch 1, for example, and I'm going to specify which fields I want. So I'm going to get flags, UID, and body. And you see that the server just responded with the message itself. But if you look at the response, see, it started with this untagged line, untagged response that looks very similar to what we were seeing in our example message. Let me pull that up here. Oh, a little too far there. Let's get this. So it starts with a star, different UID, fine, fetch, flags, UID, no flags here, so we have the parentheses with nothing in them, UID, a different UID obviously, body, and some number within the curly braces. So the significance of this is that this number within the curly braces is the size of this payload that the server gave us. So 1331 bytes. So that's good to know, because now we can leverage that because we have something like that. So it looks like what happened is some email client requested this message, and then when it came to saving the requested message, instead of starting from here, they started from here. So they just took the server's untagged response along with the payload, which they shouldn't have, but it happens. This is based on a real life scenario. So it does happen. So what does this tell us, and how can we use this? So let's do a couple of things. Number one, I'm going to go here. I'm going to make a copy of my message and open this in a text editor. And I'm going to split this part because it looks like this doesn't belong. So let's split this into a separate file, and let's close this out. So this is our file, and this is that payload. So this is 5607 characters, or sorry, 5607 bytes. And let's see how big our message itself is. This is 5874 bytes. So if we subtract, we see a differential of 267 bytes. So it looks like our message should have been 5607 bytes, but it's 5874 instead. So we have 267 bytes extra, and we know that only one complete sentence was added to the body of the message. So most likely I'm looking for a sentence that's in the realm of 267 bytes end to end. Now, would that be exact? That remains to be seen. Number one, if there was a body, if there was a text and an HTML version of the body, then that would have really made things a little bit trickier, because then there would be two versions of that sentence, and that could be some HTML tags that go with it. So that could have really complicated our life, but we're lucky in this case. There's only one version of the body, and there is no encoding or anything. So we're looking for a sentence that's about 267 characters. So I'll do a couple of things to normalize this a bit. So I'm going to take this up into a different file. There are a couple of lines where there are some extra spaces there. So I'm going to get rid of those. Essentially clear those extra lines. And then you see that this is folded. So every time you're getting close to 80 characters, the email client folded this, which is nice. You want to stay within that 78 characters as a suggestion, as per RFC 5222. So I'm going to unroll those lines. So every time there is a line break, I want to replace that with a space. So just roll this out. And now that I have just this one line, I want to break at the periods at the end of the sentences. So I'm going to say every time there's a period, give me a period and a line break. And then now I have some spaces at the front because some sentences start with a space right after the period. So I'm going to clean those out. So if there is a period and a space, just give me a period. So if there's a line break followed by space, then get rid of those. So I have my sentences here. Now, of course, there could be some edge cases here where, you know, the punctuation wasn't right, or, you know, something was off. So this is kind of, you know, hoping for the best. If it doesn't pan out, then we would re-strategize and make it a little bit more exact and thoughtful, maybe a script or whatever. But in this case, you know, it doesn't hurt to just try the simplest solution first. So we found our sentences, and I want to get this into a tool where I can measure the lengths of these easily. So let's see if I could get this into Excel. Well, the copy and paste from Ultraedit has been finicky, so I'm going to save this as a new file here. So let's call this sentences. Okay, so let's get rid of that. Sentences. Oh, that went into my other screen. Okay, so let's copy this into Excel if we can. Yeah, so this looks fine. Let's make a couple of column headings here. So let's call this sentence length. Not necessary, but so let's get our length for each line here, and let's sort this by length from largest to smallest. So here's what we have. So we have a few sentences in the realm. So what were we looking for? 267 bytes. We don't have 267 bytes. We have 283, that's the closest, and 262. Now we need to think about which is more likely to be the case. Well, if you think about it, let's say that we have this long sentence, right? And if we're going to put this into the body of this message, if you were to, let's make another copy of this here to illustrate. So let's say that I want to take this long sentence, some random sentence, and I want to add it to the body of the message here. Well, I could not copy that correctly. Let's get it from my sentences text file. All right, so let me see if I can do that. Oh. Well, Ultraedit sometimes has a little hard time copy and pasting since yesterday, so I couldn't copy it. But what I'm trying to say is, if you were to insert that long sentence into this file, because we have to break it less than 80 characters, then we're going to have to fold it. So when you hit about 70 characters or so, then you're going to have to fold and move on to the next line. So as you fold, there's going to be multiple times that you fold based on how many characters your new sentence is. So that's going to add some extra characters, the new carriage return and line feed characters. That's going to increase the number of characters you inserted. So in this case, probably the lower number is what you want, because once you add that lower number and fold, you're going to add more to it, and you're going to get closer to that 267 characters. So that would be the first one I would try. So let's find our, this will be my attempt basically. as the sentence. But let me try to find that sentence and remove it. Let's see. Let's close out of this. Okay, so we had made an extra copy of this. Let's get this open with this editor. All right, and the sentence that we had identified is 262. Let's make this a little narrower. Was this guy, the one that says which has only 2 dimensions. So let me search for that. Here, yeah. Here's a sentence that we identified as a potential candidate. So if we were to rip this out, so it starts here. And it goes all the way up to here. So it says, you know, how on a flat surface, and it ends with perspective of the thing. So it would have probably looked something like this if it weren't for that extra sentence. So let's save this and see, is our header still there? We took it out already. So let's take a look at this now. 5607. So that was 5607 in the IMAP response header. So if we take out that extra sentence, we match the payload length exactly. So that makes it easy to figure out that was the extra sentence. So again, to recap this, it was pretty straightforward. The idea here is you look at that payload size mark from that IMAP header, and you figure out which sentence is that many bytes or close to it, and try to take it out to see if it makes sense. And if it did in this case, then we're good to go. So done with Time Machine, because that was only one part. So let's close out of this and let's move on to Lucre. Let's close these guys out. All right, so this was the challenge that has been running till today, because we are starting the solutions. I archived that challenge now, so it is not rewarding any points anymore, but it is still available to solve. So here's what it says. You are investigating a financial crime where the suspects are believed to be hiding cryptocurrency private keys in email messages. That's kind of hard to believe. Most people, you wouldn't expect them to hide private keys, but it could happen, I guess, in some circumstances. An important email message is found within the forensic image of a suspect's laptop. So it is found as a local copy on a suspect's laptop. What is the hidden key? So there's a hidden crypto key there. And what is it? We need to find it. Well, let's make a new folder. And let's see if we can figure that out. So let's make this folder. Save that there. Okay, let's go look at it in our folder. Well, let's first hash it. Oh, 4784, yeah, that is our hash, so we are good there. So let's take a look at our message. Extract, open it up, let's see what it says. All right, so it's from our guy again, this guy. It's to this Yahoo email address. It has a couple of attachments. It says, hello, check these out when you get a chance. Thanks. So pretty brief message and just a little closing line and a couple of hexadecimal appearing strings here, which are interesting. And the attachment name is kind of interesting too, which looks kind of like a GUID. So let's see how we can approach this. And let's look at the attachments. So we have these two attachments, what appears to be a JPEG image and a PDF. Now, this could be kind of a rabbit hole with the PDF, because there's a lot of places where one could hide something in a PDF, especially if it's large. There's hidden metadata streams, there's just a whole bunch of stuff in there. So that's kind of concerning at first sight. And then there's the JPEG image, which also makes it possible to hide some things in there. That could be, you know, exif metadata. That could be some type of stego stuff where we hide it within the appearance of the message somehow. There could be all kinds of possibilities there. And then there's obviously the two hexadecimal strings here. That's where something could be hiding. Attachment name, it's a GUID, so I don't really see how that would be a crypto key, but could be. And then there's also the headers and, you know, the raw contents of the message. So there's quite a bit of stuff here. Let's do a quick DKIM check that verifies strict alignment. Life is good. Gmail signed off on this. So that tells us quite a bit in terms of what could have changed after the message was sent. Now, we don't know if this secret key here was hidden inside the message before it was sent or after. If it was hidden there before it was sent and DKIM verifies, then that doesn't really tell us much, because that just tells us that the message hasn't changed since it was sent, but the key was already in there. Whereas if the key was inserted after it was received, then DKIM verifying perhaps could be a little bit telling. It could tell us that, you know, none of the DKIM covered fields must not have changed since Google signed it. So that's something to keep in mind. Looking at content length matches pretty lengthy content here because of the attachments. Just to refresh your memory, content length covers the attachments as well, so all the way to the end, just as the body hash covers the attachments as well in DKIM. So that's good to keep in mind. So we can get into the message itself, but let's first explore the attachments a little bit. So let's save these attachments out first. So let me get a folder going called ATT, and let's save these attachments there. Let's see, solutions 5 ATT. Okay, so we got the attachments in here, and let's take a look at what they look like. So this is a white paper from Visa, it looks like, about NFTs. All right, so and it is 17 pages, so there's quite a bit of content here. And that could be plenty of chances to hide something there. Fine. And then looking at the JPEG, we see a photograph of what appears to be a Formula One car. Very good. So the first thing I would do is, this looks like a pretty comprehensive white paper, nicely formatted. It appears to be from Visa. So I would probably search for this to see if I can find this someplace else. And if I do, does it match what I have here? So let's do that. Let's search for that like this. Visa NFT, yeah. So Visa NFT white paper, and the file type is gonna be PDF. I'm looking for a PDF. And here is a copy of that. And let's grab a copy of that here. Let's mark this from web. And let's go compare these. They are of the same size, and they have the same hash. So that's good. That makes our life easier, because that tells us that, this is coming from the Visa website and it hasn't changed. So that kind of alleviates my concerns there about the private key potentially being hidden inside that PDF file, since it hasn't changed since Visa created that white paper. So that's a good sign. So it could be there, just as part of the conversation, or it could have another meaning, but for the time being, I'm not going to worry about that. Now, let's go back to our message. So we kind of put this NFT white paper in the back burner, focusing on these. If you look at this value here, that's actually the same as this. So that looks like that's the SHA-512 hash of the PDF. So how about this guy here? Could that be the SHA-512 hash of the JPEG? Let's do that. Let's bring that forward. And that is this hash. So that's good. So he just included the hashes of these for some reason, and SHA-512 hashes at that. But you know, the chances of manipulating the hashes in a way that he could hide something there, like a private key for a SHA-512 hash, are slim. So I can put those in the back burner too for now. If I can't find anything else, maybe I'll worry about them. But for the time being, I'm not too concerned about these hashes as they are the hashes of these files. So that's fine. So we can put the PDF in the back burner too. We can focus a little bit on the image. You could do some maybe stereotype analysis there to see if there's anything hidden in the metadata or in the contents of the appearance of the message. And you can look at, you know, what you see there within the message. One thing that I see right here is a reference to Tezos, which is actually a blockchain platform. So that's something to keep in mind, and that could be a useful reference to keep in mind when we're getting into this deeper. Right now, we're not too concerned about the specific blockchain, cryptocurrency, or anything like that, because we're just looking for a key. As long as we have like a rough approximation of what a key could look like, we should be fine. So no worries there. So I'm gonna get out of this for now, and I'm gonna postpone, you know, digging into the image, which could take more time. I'm gonna focus more on the message itself and see how I could examine this message. Now, one thing that I would do is, you know, look through this to see where something like this could be hidden. There's not much in the message body, because the message body is just plain text and there's not much to it. And the MIME boundary delimiters make sense. They're Gmail style delimiters. Message ID automatically created by Gmail API. Nothing to worry about there potentially. These headers look pretty straightforward. One thing that I would most likely do is to compare this to an example message from the same type of scenario to see if I can spot any differences. I believe I had something like that here, so let me go find it real quick and bring it. Let's see here. Okay, I think this should be it. I had made a test message. Let me open that up really quickly. So I brought it here into the solution folder. So essentially what I did was I sent a test message from Gmail to Yahoo, and essentially trying to simulate something similar. And I put an attachment like a picture. I had put it in the body of the message, just as a way to compare what a legit message from Gmail to Yahoo looks like. This is something I made a while back, but I'm just reusing it here. So I'm going to compare this. You could do something similar. So if you have a test Gmail and a test Yahoo account, you could create a control message to see how it's supposed to look and if there's something that jumps at you. So I'm going to compare these guys side by side. In this case, I'm using Beyond Compare. You could use freely available tools for this kind of differential comparison. I think WinMerge would be another option, and there's a ton of them really. So you'll see that the structure looks somewhat similar. Received by Yahoo, there's of course going to be some differences in the IP addresses, timing. The messages are pretty far apart in terms of the timing of them. But I'm looking generally at the structure of it to see if there's any extra headers, for example, or if there's anything that doesn't make sense. Now there is this Yahoo inbound spam guard header, which has quite a bit of cryptic looking stuff. So that could be a potential point where somebody could stuff something. So that's something to keep in mind, and you know, let's keep that in the back of our minds to see if the length of it makes sense. I mean, my control message and this message have the same type of shape, and they end about the same spot, so they look like, structurally they're the same, but who knows, if somebody just didn't substitute some of these bytes for something else. There's a received header, there's the DKIM signature makes sense, Google DKIM signature makes sense, message state makes sense. We have a discrepancy here. If we look at this message, which is our example message, this Google SMTP source is a single line and doesn't go very far. It's not very lengthy. If you look at our Google SMTP source, it is also in a similar structure, but it actually is folded into 3 lines. So it is presumably longer. And even though this one actually goes longer than 80 characters, it's not folded, whereas this one is. So that looks a little bit sketchy to me. So let's keep that in the back of our mind too, and let's keep going. And there's an X received header. This is also folded, whereas this one wasn't, which is interesting. But this one is longer, whereas this one is shorter, so that could explain that difference. Oh, actually, this one is folded. It's just that the tool is showing it differently because of this extra. It's trying to attribute this, kind of sync up these lines. So never mind, this one is also folded. My version, all these regular message headers and stuff, and content length, and then the body of the message. So the 2 things that jumped at me, Yahoo inbound spam guard and Google SMTP source. This is more suspicious. So let's start with the Google SMTP source and yank it out of here into text editor. Get rid of the folding, and looks like base 64. So let's throw this into CyberChef. From base 64. All right, so here's what we see when we decode the base 64. We get this. If you deal with digital forensics, and especially hidden stuff, hidden malware or malicious payloads and things like that, it pays to be kind of attuned to the magic bytes and file headers, because if you see something like that that looks like could be a file header that you would recognize, like an executable or an archive or something like that, then that could be something to act on. And in this case, this looks like the header of a bzip2 file with a block size of 9. So let's try to see if we could use that to decrypt. Actually, we could verify this pretty easily. So if we were to, for example, go zip something, 7-zip, add to archive bzip2, and look at what comes out. That's what it looks like, bzh91. So we have the same type of magic bytes, essentially, as a bzip2 compressed file. So let's see if CyberChef helps us there. bzip2 decompress, and there it is. So this is our private key. Now, if you are familiar with the blockchain or what this looks like, this is kind of consistent from this this part that this is a private key, so that kind of confirms. But even if you're not familiar, then this kind of looks like something that could be a private key, so it would definitely be my first attempt. If not, you could just keep going and looking at different things. But if you explore the photograph there, then you'll find that there is no hidden tricky thing there, but there is a reference, that was a reference to Tezos there, which is something that we should be mindful of in the next part of this challenge, which is as follows. Let's go look for that. So Lucre part 2 says, congrats on finding that hidden private key. What is the corresponding public key? Well, why would one be interested in the public key? Well, one reason is, let's say that you have the private key and you want to track transactions that are associated with that private key, right? The blockchain, the distributed ledger, keeps track of transactions tied to the public key part of that key pair. So if you want to track things, then you want the public key, so you can go after it and figure out, in a blockchain explorer, for example, what kind of transactions have taken place. So there is some value in going to a public key from a private key. And we have the private key, so presumably we should have no trouble translating this to a public key. So how can we do this? There are a couple of different ways to do this. So I'll start with one way, which I think is probably the easier way, but you can explore the other way as well, and I'm going to show you that briefly without getting into too much technical detail there. So we know of one tool that does this for us very nicely and automatically, and that is crypto wallets. Because if you have a crypto wallet and if you have your private key backed up somewhere, then the wallet can import your account based on the private key or the mnemonic phrase, but in this case we have the private key, and then it can restore your account and show you your public key. So that's something crypto wallets do all the time, and why not exploit that here and use that to our advantage. So I had seen that reference to Tezos, and there was a reference to NFTs in the other PDF, so, and Tezos is involved in NFTs as well. So I'll start there. If you recognize by looking at the private key that that's compatible, then that's great. If you don't, then you could either start there or you can explore with some other blockchains that you're familiar with, or just get a wallet that supports all of them and create some key pairs there. But anyway, I'll start with Tezos. So I want to find the Tezos wallet that I could use to restore my account or restore this guy's account to see if I can find the public key there. So let's look at what options there are for Tezos wallets. Now, if I were to look for something like that, I wouldn't search on the web because that's how you get scammed. There's all these fake wallets trying to steal people's funds, so they come up high in search rankings and in advertisements even. So you don't want to really search for crypto wallet most of the time. You want to find it from a trusted source. So I would look for that in the Tezos Foundation website. So it says if you want to store and use Tezos, you could use one of these software wallets. Now, I don't want to deal with installing an application right now or getting into my phone or anything like that. So I'm going to look for a web wallet, and I'll use Temple Wallet. All right, so it looks like this is something that could be downloaded as a web extension for Chrome. Let's see. Yeah. All right, so let's install this here. And let's make this pin so we can see it. All right, so it says create new wallet or import existing wallet. So if we were to import an existing wallet, it's asking for a seed phrase, so a mnemonic phrase and a password. We don't have the mnemonic phrase for this guy. It might be possible to derive that somehow, and I don't really know the format of what this key store file would look like. So I'm going to skip that. I'm going to create a new wallet. So let's keep track of what we're doing here. So let's create a new text file here. Since we're doing this just for testing, so I'm going to create a random password here. Oh, well, not secure enough. We need something uppercase. Repeat the password, accept the terms, create. Now let's reveal this mnemonic phrase. I made a backup, yes. So it's asking to confirm the backup, so it's asking for word 2, so I'm going to put that there. And word 10 before moon, that is going to be this guy. Okay. So I'm creating a new wallet now, but that's not really what I'm going to use here. What I want to do is I want to import an account based on a private key. So I had found my private key, right? Where was my private key? And if I import my private key here, now here's my account 2 imported from that private key, and here's my public key that corresponds to this account. So this was an accepted solution. Now some of you might be thinking, well, that's not what I did, which is fine, because there are multiple ways to do this, and this is actually a little bit of a massaged version of the public key. There's like a Blake here and base 58, and there's a bunch of data massaging going on to get to this TZ form of the public key. Now some of you might have taken a more purist approach and kind of cut out this Tezos ecosystem and work directly with the key pair. Essentially, there's a way to create a key pair, there's a way to derive a public key from a secret key and all that. And if you did that, then that would look a little bit different. So let's take that approach now and see how we could accomplish something like that. So I'm going to close out of that, and I will have my key pair there. So for this, I'm going to use a programming language. I'll use C#. You could use Python or anything like that. There is going to be a crypto library that we're going to use, and that is essentially salt. So let me bring that to view here. So this implements some very valuable crypto functions and supports this signature algorithm, which is also used in SSH, and it's used in this Tezos keys as well. And I'm going to be using a C# fork of this salt library called libsodium, so the sodium library. So I'm going to add that as a package, and I'll go from there. So let's create a new, and I will use this little tool called LinkPad, which is pretty good for, what did I do there? LinkPad is pretty good for prototyping, so I'm not going to fire up, full-on Visual Studio there. I'll make a little query here, and I will save this. So let's go find my solutions for 5. Let's call this crypto solution. All right, something like that, and change this to statements. And I'm going to add a couple of NuGet packages. You could do something like this, in Visual Studio or in Visual Studio Code probably. I'm just going to use this because it's pretty handy. So one of them is libsodium.net, I think. Yes, so I'll add this. And the other one, base 58, check. Yeah, so libsodium is essentially a fork of that salt library. It's essentially similar functionality, but available for C#. So I've added my 2 packages, and I'm good to go. So what I want to do is, one thing that you should know is that I've looked at this Tezos source code here, because there are some magic bytes that they use. So base 58 essentially allows you to pin down a few bytes to the start of the result, and Tezos uses some magic bytes that are listed here for public keys and secret keys. So you can refer to this to figure out which magic bytes are needed for this exercise, and I'm going to show you as we go along. So I'm going to start by let's see, defining my secret key that I had found. So let's go to this guy here. So let's call this secret key. So that's my secret key. Now I'm gonna so this is a string right now. I'm gonna turn this into bytes. So if I were to call this secret bytes, now I'm gonna tap into that base 58 library, base 58 encoding. Let's go here, decode, and secret key. Okay, so let's take a look at what secret bytes looks like right now. So this is my byte array for the secret key, but the first 4 bytes of this is actually magic bytes. That's based on the information we find in Tezos source code. So we want to strip those before we do some more conversions on them. So I can do that pretty easily. Let's call this, well, let's actually do that right here. So let's skip the first 4 bytes and get the array here. So going back here, you'll see that we should start with 176 now. All right, so we skipped the first 4 bytes that were the magic. So now we want to get the public key. So to show over to public key, let's go this public bytes. This time we're going to use sodium. and extract, no, sodium public key auth, extract public key from secret key, and we're gonna use our byte array secret bytes there. Let's dump this to see what that looks like now. That looks kind of like this. And then now to get the public key itself, we're going to actually add some magic bytes. So the magic bytes for the public key look like this. I'm going to copy this here. You'll find this in the Tezos documentation. So I need to add this to my public bytes. So let's create our public key. We're going to use this base 58 check. This time encode, and we're going to concatenate the magic bytes with this public bytes that we found. So let's say magic public dot concat public bytes to array. So that should be my public key. Let's see if that worked out. And that is the alternate solution. So in this case, what we did was we stripped out the magic bytes in the secret key and derived the public key from it, and then put back a different set of magic bytes and created the public key in the format that Tezos uses. This was also an acceptable solution, and quite a few of you actually used this, which was surprising to me. I was expecting a lot more of the first solution than this, but fine either way. So this was the second way to go about doing this. In any case, that concludes the solutions. Like I said, the challenges are going to keep coming. So this was challenges 1 through 5. So right now we have archived all of them, and you should expect a new challenge probably later today, challenge 6. And we should hold a similar event at the end of challenge 10, where we will explore challenges 6 through 10 and go from there. And that's it. So if you have any questions, feel free to drop them there. If not, you can reach out to me via email or LinkedIn or something like that, and we can chat some more there. You should expect some more challenges coming very shortly again. And thanks again for joining. I'll wait for a minute or so for any questions. If not, we'll wrap up. I see that we've gone a little over, I think, but close enough. In the meantime, let me have a little water. All right, no questions. So I assume it was well received and everything is clear. So I'll wrap up